So in my previous lectures, we have discussed what are the different way to handle different construct for structured programming like sequence, selection, iteration and function call, and how we can apply the unified machine model concept to carry out the analysis of these four constructs. In this lecture, I will concentrate on different asymptotic notations. Let us formally define those asymptotic notations. First is big O. Let a function fn is said to be big O, another function gn. Fn is the analysis of one algorithms, gn is another analysis of another algorithms. Fn is said to be big O gn, we can call it as order of gn. If and only if, IFF. Now what is if and only if? This means both necessary and sufficient conditions. If and only if there exist two positive constant, there exist two positive values C and N0 such that for all n greater or equal to N0, the value of Fn is always less equal to C into Gn. Now what does it mean? The value of C into Gn, C is a positive value, positive constant. So C into Gn, this value is always above Fn. Now let us interpret this graphically. Suppose we have plot n along x-axis and time. Here time means the unit count, because absolute time is meaningless in this case. The unit count for Fn and Gn both. If we plot this, let the Fn is plot like this. Let this is Fn. And value of C into Gn, let the value of C into Gn is something like that. Let this is C into Gn. So what we observe from this? If we consider for all n which is above this point, if we consider this is our N0. So what we found, that all values of n greater than this N0, the value of C into Gn is always above Fn. So this is the value of Fn for all n greater than N0, and this is the value of C into Gn. C into Gn is always above for all values of n greater than N0. Now what is the physical interpretation for this? Suppose we have developed an algorithm, and this analysis of this algorithms is represented by Fn, and Gn is some well-known algorithm whose behavior, time, total time is well known to us. We want to compare whether the algorithm which we have developed, that is of the order of that algorithms or not, well-known algorithms or not. If I say, if I able to say that Fn is equal to big O Gn, that means we can conclude that the running time of the developed algorithm will never exceed than that of the well-known algorithms Gn. So we can say that Gn is the upper bound of Fn, and we call this as asymptotic upper bound because here we have ignored the constant and we are interested for the behavior of the algorithms for larger value of n. We are not interested for the behavior for this side. This lower value of n will not give you the actual picture. We are analyzing this behavior of the algorithms for larger values. That is the significance of asymptotic notations. That is the motivations for asymptotic notations. Okay. Now, if somebody says that Fn for, we have already calculated Fn for matrix addition as 2n square plus n plus 1, and let Gn is given as n square, where n square can be like the running time for a bubble sort. Bubble sort runs in n square time, where n is the number of elements. Now, in this situation, can we able to say Fn is big O Gn? So, to do that, we require to find out a constant C and n0 such that we can say Fn is greater or equal to C into Gn. Now, let us find that. We can always say Fn is equal to 2n square, as it is given, n plus 1, that is given. So, I can always say Fn is less equal to 2n square plus n square plus n square, even if n is greater or equal to 1. Because if I replace this n by n square and 1 by n square, then even if n greater or equal to 1, this value is definitely less than this value. So, we can say Fn is less equal to 4n square even if n greater or equal to 1. So, this is our C and this is our n0. So, we have found out one constant C and another constant n0 such that this inequality is satisfied. So, we can say Fn is equal to big O n square. Now, if somebody says that Fn is big O n to the power 3 or Fn is big O 2 to the power n, then also it is correct, because any function which lies above this Fn, for those functions this big O notation is true, because that will again be the upper bound of that. So, if I have another functions like this, say some constant C into Hn, that is also work as an upper bound to Fn. So, any above value which lies above this Fn, for that big O notation is satisfied, but which is accurate? So, in case of upper bound, we are interested for the upper bound which is very close to Fn, that means the least upper bound. Least upper bound. So, in case of big O notations, we will always require or intend to find out the least upper bound. Next, let us come to big omega notations. Now, what is big omega? Denoted by this sign. Let us formally define big omega. Fn is said to be big omega Gn if and only if there exist again two constants C and n0 such that the value of Fn is always greater or equal to C into Gn for all n greater or equal to n0. just it is opposite to big O. In case of big O, that is less equal to, and in case of big omega, it is greater equal to. Now let us interpret this graphically. So if I say the plot for Fn, this is n, this is time, that is Fn and Gn we are plotting along this direction. So if I say this is Fn and value of C into Gn is this, let this is C into Gn. So you just observe C into Gn is always below Fn. That means we are approaching towards Fn from the lower side for all values of n greater than this n0. If I said this is n0, so for all values of n greater than n0, the value of C into Gn is always below Fn. That means we are approaching towards Fn from the lower side. So if I say that Fn is the running time for the algorithms which we have developed, and Gn is some well defined algorithms, well known algorithms whose behavior is well known to us, then we can say the running time for the algorithms for which we have developed the programs, or we have developed the algorithms, for that it will take at least the running time of Gn. That means it will take, this Fn will take at least the time as that of Gn. It will take at least this much of time. So we can say that Gn is the lower bound of Fn. Now let us take the previous examples. For matrix addition problem, we have said that Fn is equal to 2n square plus n plus 1, and let Gn is the complexity for or running time for bubble sort, that is n square. In this situation, is it possible for us to say Fn is equal to big omega n square, or that means Fn is equal to big omega Gn? Is it possible for us to specify? Now let us see. Again, we require to find out a C and a n0 such that this inequality is satisfied. So we can write in this way, Fn is equal to 2n square plus n plus 1. That means we can say this is always Fn is always greater or equal to 2n square, no harm, because if we truncate this part, then definitely it has some positive contributions. So Fn is greater or equal to 2n square. So this is our C, and this is true for even n greater or equal to say 10. So this is our n0 and this is our C. So this inequality is satisfied, Fn is greater or equal to C into Gn. So again we can say for Gn is equal to n square, Fn is big omega n square, that is satisfied. So this is the concept that by big omega we are specifying the lower bound, and big O we are specifying the upper bound. Now in this case, in case of lower bound, by the same logic we are interested for the lower bound which is very close to Fn. That means the greatest lower bound, because any lower value, for any lower value, this big omega notation is true, because that is greater or equal to that that Hn. Suppose if this is Hn, if this is Hn, some constant C into Hn. So again we can say Fn is equal to big omega Hn, but which is more accurate? More accurate in this case is Gn, because Gn is greater than Hn. So in case of lower bound, we are interested to find out the greatest lower bound. We are interested to find the greatest lower bound.